Alright, let's start off by going over the electron energy and light assignment. I'm going to try and go through this quickly because we have a lot to do today, and I'm going to try not to go off on tangents like I usually do. Our objectives for this activity: we should be able to describe the relationship between energy, wavelength, and color of light. Turns out if we know two of these things, we can calculate the third thing. And we can describe the interaction of light and electrons and atoms. There's a relationship in there. We got to find it. And we can explain how the lines in an emission spectrum relate to the energy levels of electrons in the atom. So when we get to that part, we should be looking for a connection between the lines in the spectrum and the energy levels of electrons. So, from fireworks to stars, light is very important in our life. We use light at night to see, so it's not dark. Our TV makes light so that we can watch our shows. Fireworks make light, right? So light is a big part of entertainment. Light is everywhere. It's very important. And so we are going to do some discoveries about the nature of light. The first thing I wanted you to do was kind of play around with light a little bit by going to this simulation. And I asked you to play around with these tools until you could get this light to bend. And this was the one that I liked the most, was this configuration right here. You can see that the light is bending a lot, but that's not the only configuration you could have used. It doesn't work very well. Ooh, weird. Anyways, it's not really bending the light, is it? Does this one work? That works a little bit. I can see it bending down here, but the best configuration is this one right here. You can see the light is spreading out. I'm sure you remember from previous classes that white light is a mixture of all the colors. And so what's happening here is that red, orange, yellow, green, and blue and violet is getting separated. It's getting bent. And the reason it's getting separated is because the colors are not all bent equally. So which colors are getting more bent or more refracted? Well, it looks like the red is getting least bent, and the purple is getting the most bent, isn't it? So we'll come back over here. Here's our model. Light source, prism. The light is coming out. Which color of light was the least refracted or the least bent? Well, that was red that was least bent, right? And then which color was the most bent? It was violet. And then we need all the colors in between. Looks like yellow was bent a little bit more than red. And orange, orange, yellow. Well, right. We know that it's red, orange, yellow, right? From the song. Red, orange, yellow, green, blue, purple. Red, orange, yellow, green, blue, purple. So rather than me having to come back and fix all these, let's just do it right the first time. Red, orange, yellow, green, blue, violet. Okay. And you don't have to determine the numbers, the photon energy and the wavelength range, because it's already in there. If you can figure out which color is the least refracted, then you know that color goes with this information. And I asked you to type in the names of the colors Now, when you look at this, even though it looks red, there's actually lots of different shades of red in there, aren't there? So there's actually more than one red there. And there's more than one yellow, and there's more than one green, and more than one blue, and more than one violet. And so it's actually, this group is actually the reds, the oranges, the yellows, the greens, the blues, and the violets. And I asked you to go ahead and color these rows with the respective colors. Coloring on the computer is not quite as fun as coloring in real life, huh? Alright, red, orange, yellow, green, blue, violet. And then after this, you should have gone on to the next slide. And oh, I gave you the answers. I wanted you to look at this and come back here and check your work and make sure that you got the right answers. Because if you don't have the right answers, you're going to be moving forward with some incorrect assumptions. So double check, make sure that you got red, orange, yellow, greens, blues, and violets. Alright, now some questions for you. What happens to white light when it passes through a prism? It gets refracted. And separates into different colors. Obviously, lots of things you could have put there, but that's basically it, right? If I wanted to be more thorough, and separates into different colors because different colors, or because each color, let's say, bends a different amount. There we go. That's more specific. That's more complete. Why are the color labels in the table in Model 1 plural, i.e. reds rather than red? You might not have put reds in yours, or oranges or yellows, but that's another reason I wanted to put this here for you, was so you could see that the correct answer was reds, oranges, and yellows. So why is it reds, oranges, and yellows, and greens? Why is it plural? No, because they're plural because there's more than one shade of each color, right? According to the table, do all colors of light travel at the same speed? Well, let's go look at our data. Speed, 3.0 times 10 to the 8th power. 3.0 times 10 to the 8th power. 3.0 times 10 to the power. Well, yeah, even though these numbers are different over here, the speed is always the same, according to this chart. So according to the data, according to the table, all colors travel at 3.0 times 10 to the 8th power. Were there units over here? Yeah, meters per second. So yes. And make sure you come in here and go to Format Text Superscript. because 10 to the 8th is not the same thing as 108. According to the table, do all colors of light have the same energy? Remember, energy is measured in joules, so if you are confused as to which one of these is energy, you can look for the units. Joules. Ah, this is in joules, it must be energy. Do they all have the same energy? Well, a quick glance will tell you that no, they do not. If not, which colors have the highest energy and the least energy? Which ones have the highest energy? Well, 452 and 523 are much higher than 269 and 318, right? So, red has the lowest numbers, so it probably has the lowest energy. Violet has the highest numbers, so it probably has the highest energy. Which color corresponds to the longest wavelength? Which one has the longest wavelength? Well, if you were measuring a wavelength to see how big it is, and you got a high number, would that mean that it's short or long? Well, I think you'll agree that if you measure something, if you measure its size and you get a big number, well, that means that it is long, right? So, which has the longest wavelengths? Reds have the longest wavelengths. And which color has the shortest wavelengths? Well, I think I already know what it's going to be, but yes, violets have the smallest numbers, so they have the smallest lengths. Does that surprise you? Does that surprise you that violet has more energy than red, and it has the shortest wavelengths? All right, considering your answers to 5 and 6, write a sentence that describes the relationship between wavelength and energy of light. Many things you could put here. You know, one thing you could do, and I'm just pointing this out, you can always come back up here to these objectives and see if there's anything you know, that looks important here and might help you with your answers. Energy, wavelength. Actually, I don't think that's very helpful, so never mind. Write a sentence that describes the relationship between wavelength and energy of light. Well, it seems to me energy and wavelength. It seems to me that when wavelength is big, energy is small. And when wavelength is small, energy is big. Do you remember what we call that when there's a relationship between two things and one gets smaller as the other gets bigger, or one gets bigger as the other one gets smaller? So basically they're going in opposite directions. So instead of going with each other, they're going opposite of each other. Do you remember what kind of relationship that is? That's called an inversely proportional relationship. Instead of going with each other, they go opposite of each other. See, let me think here. Is there any details that I left out? Is there any way I could make this answer better? I don't think so. I think that's good enough. Alright, what is this? Model 2, emission spectra for hydrogen and boron. Okay, there's two elements, hydrogen and boron. Alright, what am I looking at? What the heck is this? Oh, here we go. What am I looking at? In this model, imagine we have taken pure hydrogen gas and put it in a glass tube all by itself. And that's what this was supposed to be, by the way. I hope you got that. Hydrogen gas discharge tube. Then we run electricity through it. Bzzz. It produces bright light similar to a neon sign. We put two plates with narrow slits in front of the lamp. So if this is the lamp here, then these would be our slits. They're just little slots that have been cut out of these two plates. Almost looks like you could put a quarter in there. So we put those slits in front of the lamp, and the light travels through those slits. Of course, it's getting blocked by the plates mostly, but a little bit of that light goes through the slits. And the only light that goes through those slits are the wavelengths of light that are going up and down. Up and down. The wavelengths of light, when you have something like this and the light is coming out, the light comes out in all directions. It might be horizontal, it might be vertical, and everything in between. So this is kind of like a filter, and it gets rid of all of the left to right light, and it only keeps the up and down light that goes through. So by the time it gets over to here, all of this is up and down light. The light travels through the slits and then through a prism, just like in our activity from before. And then what does the prism do to light? Well, it bends it. And it bends different colors by different amounts, right? Reds are going to be less bent. So just by looking at this one over here is less bent. So this is probably a red. And these ones over here are more bent, so these are probably more like green, blue, or purple. Actually, purple's probably way over here, but green, blue, or purple probably. And I haven't even looked down here, so we'll see that in a minute. But, so it goes through a prism, and then the light lands on an instrument that detects wavelengths of light. This line spectra tells us which wavelengths were detected. So this light hits this instrument over here, and this instrument kind of takes a picture of that. And here are the pictures down here. This is the picture for hydrogen. And then this is the picture that would have come if we took this out of here and we put a boron gas tube here and then ran electricity through it. And then that light goes through the slits and through the prism and to the instrument. Well, then the light that goes through there is going to be different. It's going to hit different spots. And how do we know that? How do we know that the light is going to hit different spots? Well, because early scientists did these experiments. And this is what they found. They found that hydrogen always shows a line here at exactly 410 nanometers. And another form of light that comes out is 434 nanometers. And some more light comes out, and that's 486 nanometers. And some more light comes out, and that's 656 nanometers. Oops, did I do the wrong ones? I might have said the wrong ones. Let's see here. Red, that's this one, because it's less bent, right? And then blue-green. and then blue violet, and then violet. Sorry, I got those mixed up. Now, is there any light at 415 nanometers coming out of this tube? Well, not according to this. According to this, there's no light here. There's no in-between light happening here. And there's no in-between light happening here. There's no in-between light getting picked up over here, or any light getting picked up over here. Only a little bit of light at 410 nanometers, a little bit of light at 434 nanometers, a little bit of light at 46, and a little bit of light at 656. I shouldn't say a little bit of light. It's probably lots of light. But, you know, it's only coming out here. There's no light coming out at 600 nanometers. There's no light coming out at 658 nanometers. There's no light coming out at 666 nanometers. It's just these four. And when you put a different element in here and run electricity through it, you get a totally different line spectra. And it turns out that you could take all of the elements and run electricity through them and do this exact same thing, and you would get a completely unique line spectra for each element. That's what the early experimenters found. Alright, what do I do? Use shapes or the line tool to color the lines on the line spectra. The line at 410 nanometers should be colored violet. The line at 656 nanometers should be colored red. Alright, a couple ways you could have done this. My tool tip here. I had a little trouble figuring this out myself, but you can actually come up here to the line tool and go to scribble. And then this will allow you to draw on here, basically. And I can hold the left mouse button down and then release it. And then afterwards, that's when I choose the color and choose the line width. And there we go. So you could do it like that. Another way you could do it is just do a little shape. Just do a little rectangle here. And make sure you turn the border color off and then fill that with, what is this, blue-green? That's kind of a blue-green right there. And then if you do it this way, you can just Control, Copy, and V. And I'm using the arrow keys, but do you see how it jumps around a lot when I use the arrow keys? Actually, it looks like it's lining up perfectly, which is great. But if you don't want it to jump around so much every time that you press the arrow key, you can hold the Shift key down, hold it down, don't let it up, hold it down, and then when you use your arrows, look, it's much smoother. Just moves it by a little bit. So that can help you line things up if you want. Now this one is not blue-green, this one is blue-violet. Well, there's not a real great option for blue-violet, but well, if there's a color that you want that's not here, what can you do? This is blue, this is purple. How do I choose something in between? We can come down here to custom color. And then here's blue, here's violet. Let's try and find something in between blue and violet. That's kind of a blue-violet, I would say. And there you go. And now violet. Control copy, Control paste. And purple should be fine there. Doesn't look like a huge difference, but that's okay. There you go. Boom. Lines colored. Also color the lines on the spectra for boron. Oh, crud. Alright, well. Control copy, Control V. Actually, I could just Control copy V. Even though these are different reds, I don't really care. So this is 656 nanometer red, and this is 625 nanometer red. They're different reds, but your eye probably can't even pick that up. Let's see, we need an orange. So here's a line, go to orange, and Control Copy V. Grab this and put it right there. Blue, green. Actually, if you wanted to, you could just copy this guy. Control Copy V. This needs to be blue. Control Copy, Control V. Blue, blue. Oh crap. There's two blues. Well, this one is going to be more of a red blue, right? So a lower energy. So if we just go to our custom colors again, go to blue. If we just move it a little bit more, oh geez, this is confusing. Alright, so in this graphics program there's red on both sides, but you know that from electromagnetism, right, the thing in our activity, you know that blue and purple are on the opposite side of red. So if we're trying to get a blue that's a little bit more towards red, you need to go this way, not this way, okay? So we're going to get a blue that's just a little bit more towards the red, then that would probably be good, something like that. Control C, Control V, and a bunch of violets, right? Honestly, I don't even care if you just make them all the same. You know that they're different. And I'm using the arrow keys because I think that's easier right now. And it looks something like that. Good enough. Alright, what are we looking at here? Okay, well, now this looks familiar. This is just the same thing from here. This is hydrogen, hydrogen, and boron. List the spectral lines for hydrogen gas by color and corresponding wavelength. So the first one is at violet, 410, blue, violet, 434 nanometers. Blue, green, and red at 656 nanometers. Okay, I think we're done. There's only 4 there. Next, spectral lines for boron were produced using the same method as hydrogen. List 3 of the colors and corresponding wavelengths for boron spectral lines as its light passes through a prism. List 3 of the colors and corresponding wavelengths. So that's just going to be the same. 3 colors. You can choose any 3 that you want. Let's just say red, 625 nanometers. Orange, 609 nanometers. And blue, green, 499, not 500, 499 nanometers. And we are done. Number 10, consider the hydrogen spectrum above. That's this one. Remember, this is hydrogen. This is boron. Which color of light corresponds to the shortest wavelength? Well, if you remember earlier, and it's okay if you don't remember which one we said, you can always go back and look. We said that Reds have the longest wavelengths and the lowest energy. So which color of light corresponds to the shortest wavelength? The shortest wavelength. Wavelength. Well, we said that a smaller number means that the wavelength is short. If we measure it and it's a small number, then it's short. So the shortest wavelength should be violet, right? Which color of light corresponds to the longest wavelength? Well, looks like red is the longest. If we measure this red wave and it's got a higher number, then it's longer. Okay. Consider hydrogen above. Okay, we're still talking about hydrogen. Which color of light has the most energy? Well, red has a higher number, so does that mean that it has more energy? Bigger number means more energy, right? Well, no. We said that they were inversely proportional. Reds have low energy, violets have high energy. So actually, violet has the most energy. Which color of light has the least energy? Well, that's going to be red. Now, is this going to be true for every element all the time? Is the answer always going to be violet and red? Well, no. Why? Well, because I said that every time you put a new element in here, you're going to get a unique spectrum. And one particular element may not have any violet. It may not have any blue. Maybe it only has lines over here on this side. And so maybe that element's highest energy wavelength, maybe that highest energy one is going to be green. So you have to look at the spectrum. All right, least energy, red. Next meme. So I included these answers just to make sure that you were on the right track. All right, does a gas tube filled with boron, we're talking about boron now, emit the same wavelengths of light as a tube filled with hydrogen? Well, it's not enough to just know the answer. You have to be able to explain the answer. So, does a gas tube filled with boron emit the same wavelengths of light? Well, you can see right here that no. They're different wavelengths of light. How do I explain that, though? No. Boron emits different wavelengths of light from hydrogen. How do I explain it? How do I explain it convincingly? If you look at the two spectra, the colors, wavelength, measurements, you don't have to put measurements. Colors, wavelengths are different. That's good enough. The spectral lines for elements are like fingerprints for humans. How do the spectral lines for hydrogen and boron support this statement? So you're going to use this as evidence for your answer here. Fingerprints are so unique that they can be used to identify people, identify individuals. Similarly, the line spectra for each element is also unique. So the line spectra could be used to identify individual elements. We used fingerprints to determine whether a particular individual was in a particular place, or whether they were holding a particular weapon. Right? That's our evidence. It's our evidence they were there. Similarly, line spectra are the fingerprints for the elements. If you can find a line spectra for hydrogen, then you know that there's hydrogen there. If you can find a line spectra for tungsten or gold or helium, then you can say with reasonable certainty that there's helium there, or there's gold there, or there's tungsten there. And this is why we can say with certainty, this is how we know what stars are made of. We can't go there and collect samples and analyze them, but we can look at the light that is coming from the stars, and we can look at the fingerprints for each element, and we can say, oh, okay, we know exactly which elements are in that star. Alright, circle with circle shapes. Everything's a little bit more difficult on a computer. Most appropriate word to complete the following statements. Electrons and protons. Electrons are negative, protons are positive. What do negative and positive want to do? They want to attract each other. As an electron gets closer to the nucleus, the attraction to repulsion from the nucleus gets stronger, weaker. Alright, I suppose you could put repulsion gets weaker, but it makes more sense to say that the attraction gets stronger, because you said that they attract each other. So electron is negative as it gets close to the nucleus. It's closer, so it's pulling. They're both pulling on each other more. For an electron to move from an energy level close to the nucleus to an energy level far from the nucleus, it would need to gain or lose energy. Gain or lose. Well, maybe one way to think about this is, would you rather hike up a hill, or would you rather hike down a hill? Now, some of you, you're like, oh, I like to exercise. I'd rather go up the hill. Okay, whatever. But it's easier, right? It takes more energy to hike up the hill than it does to hike down. And since electrons want to be close to the nucleus and they don't want to be far away from the nucleus, okay, then the electron would have to gain energy. Okay, we would have to take some energy and we would have to give it to the electron because it's going uphill. You need more energy to go uphill than you need to go downhill. So some energy comes in, the electron absorbs it, and it's in a high energy state. And I gave you the answers again so you could check yourself. Didn't want you going forward with any incorrect assumptions. All right, stop. Read this. Niels Bohr modified Rutherford's nuclear atom model to explain how light interacts with electrons in an atom to produce spectral lines. Those are the fingerprints that we just talked about for elements. Niels Bohr's model included electrons orbiting the nucleus at specific energy levels. Electrons absorb energy from various sources like electricity when they move from lower energy levels to higher energy levels. Energy is released as electrons return to their lower energy levels. So if a wave of energy, okay, remember that energy that we said was part of the colors, right? Red light has energy, but not as much as violet light, but they all have energy. And so if the atom is sitting there and all of a sudden a bunch of energy slaps into that atom, well, where's that energy going to go? That energy is going to excite those electrons. And they're going to ride that energy up into higher energy levels. And we call that being excited. But they don't really want to stay there. Remember, they want to be close to the nucleus. They don't want to stay far away from the nucleus. So, as soon as they can, they're going to come back in towards the nucleus. And just like they absorbed energy when they moved away from the nucleus, now as they move toward the nucleus, they emit energy. And that is where light comes from. Light comes from electrons getting excited, and then they don't want to be excited, so as soon as they can, they give that energy off in the form of light. Alright, so what do you think is happening in this model? Well, it probably has something to do with what we've been talking about. This is probably not a target at the shooting range. It's one of these three things. Is it an electron is moving from ground state to an excited state in an atom? Well, okay, what's ground state and excited state? Lower energy levels, ground state. Higher energy levels, excited states. So it looks like the electron is moving away from the nucleus, so these must be the higher energy levels on the outside. And these must be the lower energy levels on the inside. And so it looks, this arrow, if this arrow means that something is moving from here to here, could this mean that an electron is moving from a ground state to an excited state? I think it could be this one. Let's see what these other ones say. An electron is leaving this atom forever. I don't think so. A proton is growing larger and larger. No. So let's type in an electron is moving ground state to unexcited state in an atom. Okay, an electron is moving from a ground state to an excited state. Is energy absorbed or released for this electron transition? Well, what do you think? Is energy absorbed or released for this transition? Well, I said that in order to get that electron to move uphill, it's gonna have to it's gonna need some energy for that, right? So this is one of those cases where the energy comes in, whoosh, and that extra energy makes that electron go out. You could say up, but you know, it's a circle, so I feel like out is more accurate. So that electron goes out. But then it doesn't want to stay there. Remember, it wants to be close to the nucleus. So as soon as it can, it gives off that energy in the form of light, and it comes back down. Now, we're not seeing that here, but that's what it's going to do. So is energy absorbed or released? Ugh, I have to explain this? Ugh. All right. Energy is absorbed. Energy is absorbed. Energy is absorbed because the electron would need extra energy to move away from the, or to move against, you could put move away, but I think move against, to move against, let's put move outward against its attraction to the positive. Let's be as specific as possible. Because the negative electron against its attraction to the positive nucleus. All right, I like that. I'm proud of that answer. All right, what are we looking at? In this model, the arrows indicate electrons moving from either a low energy state to a high energy state, or they could be moving the other way. They could be moving from a high energy state to a low energy state. The energy levels are numbered to help you answer the questions. The energy level on the inside is numbered 1 because it's the first energy level to get filled up. And that's because of that whole thing about electrons wanting to be as close to the nucleus as the laws of physics and the other electrons will allow. So after the first energy level is full, then other electrons start filling up the second energy level, and when that's full, then the electrons fill up the third. It's kind of like seats at the movie theater. And now not everyone always wants to sit in the front row, but there are certain seats that are more popular. A lot of people like to sit in the back. A lot of people like to sit in the middle. And if you are early and the theater's empty, well, then you get first choice. You can sit whatever you want. But I don't know if you guys have ever been to a movie where that was like all sold out, and maybe those were the only seats that were left, was the front row seats. You take what you can get, but that's not really where you'd like to be. So the first electron levels fill up, and if you're late to the party, then you get the sucky seats. If an electron is as close to the nucleus as possible, that is, as close as the other electrons will allow, the electron is happy and in a low energy state. If something takes the electron far away from the nucleus, like a sudden burst of energy, the electron is excited and in a high energy state. Don't think of excitement as a good thing. Electrons don't like to be excited and go back to the ground state as soon as possible, discharging new energy in the process. What is that new energy? No, that's light. That's light, and actually it's ultraviolet light and it's infrared light too. But we can't see that stuff. The only stuff we see is visible light. Alright, what do I do? Identify with the arrow the drawing that depicts a hydrogen atom with an electron moving from energy level 5 to energy level 2. Alright, so that was supposed to be an arrow right there. Actually, now that I'm looking at it the way you guys probably saw it, looks kind of more like a magnifying glass, doesn't it? Probably should have made that arrow a little bit more distinct. But what I wanted you guys to do is to basically like highlight one of these based on which one is depicting a hydrogen atom with an electron moving from energy level 5 to energy level 2. So 5 to 2. Well, 5 would be outside of 2, and 2 would be inside of 5. So it's probably going to be an arrow going in. Oh, they're all going in, aren't they? Well, which one is 5 to 2? Fortunately, they're numbered. This one is 5 to 2. Oh, well, this is it then, I think. Let's take a look at least at one other one. This one is, okay, level 4 down to level 2. So, yeah, I think this is it, this one over here. All right, this one, electron transitions. What do I do? Each atom has a blank line above it where the label should be. Okay, so that's here. Find the atom with an electron transitioning from the 5th level to the 2nd level. Same one you identified in the previous slide. Okay, so that was this one, right? And label it N5 to N2. N5 to N2. And this is how we express electron transitions. Okay, we're not going to draw this model every single time. We're just going to say N5 to N2. This is where it starts. This is where it goes. Finish the labels for the other drawings. Well, let's see. This is N6 to N2. This one is 4 to 2. And this one looks like it is 3 to 2. N equals 3 to N equals 2. Try to match the colors in the spectra to the drawings. Okay, so this is, oh, there's no label here. That's a bummer. But these are all hydrogen atoms. It says right here. These are Bohr models of hydrogen atoms. And hopefully you recognize this from our discussion of hydrogen spectra. So how are we going to match the colors to these models? We're going to have to use a little bit of logical thinking. Red, we said, has the longest wavelength. Which one of these has the longest wavelength? This one has the longest wavelength, right? These ones have short wavelengths. This one's longer and this one's longer, but this is the longest. So this probably matches the red line. So I'm going to put red for now. I can always come back and change it. This one has more energy, but not as much as these two. So its wavelength is going to be shorter than red. So this one is shorter than red, but it's longer than these two. So I'm going to guess this is the blue-green. And if you use that logic, you should be able to figure out that this is blue-violet. And this is just violet, our shortest wavelength and our highest energy. Uh-oh, got a little messed up here. Oh well. In electron transition A, that's this one, is energy being absorbed or released? Well, what do you think? Is energy being absorbed or released here? If that electron is going from the outside level to the inside level, is energy being absorbed or released? Well, hopefully you said released because the electron is moving toward the nucleus. In electron transition A, is the electron moving from a low energy state to a high energy state, or the other way around? Well, we said when the electron is far away from the nucleus, it's excited, and it doesn't like that, and it would rather come inside. So that means that it's going from a high energy state to a low energy state. And why is that a high energy state? Well, remember, that only happens when the atom absorbs energy. So that's a high energy state. It's going from a high energy state to a low energy state. And for D, is energy being absorbed or released? I don't know. What do you think? Is energy being absorbed or released here? The electron's moving from N3 to N2. Well, this is no different from Model A. It's going from outside to inside. This is going from a higher energy level down to an inside, a lower energy level. So I think this one is released again. Released. Because the electron is moving toward the nucleus. Is the electron moving from a low energy state to a higher energy state? Well, it's the same thing as before, right? Anytime the electron moves out, it's going from a low energy state to a high energy state. Every time the electron moves in, it's going from a high energy state to a lower energy state. Probably I shouldn't say high or low. I should say higher and lower. Because all of this stuff is relative, right? Is n equals 3? Is that a high state or a low state? Well, it depends on where it's going, right? If it's going from N3 to N6, well, in that case, N3 would be a lower energy state. But if it's going from N3 to N2, then in that case, it's going from a higher state down to a lower state. Which of these transitions involves the most energy? Which of these transitions involves the most energy? So this could be absorbing or it could be releasing. Doesn't really say. However, all of these are releasing energy, so it really doesn't matter. Which one is releasing the most energy? Well, there's a couple ways you could go about this. You could just remember that the shortest wavelengths have the most energy. So you could say A is releasing the most energy because it has the shortest wavelength. There's another way of looking at it, though. Isn't the electron in Model A traveling the farthest? The electron in Model A is going from N6 to N2. None of these other ones are making as long of a journey. So that long journey involves the most energy. And the same thing if it was going from here down here up to here, that would absorb the most energy, right? That would absorb the most energy. So coming down from there releases the most energy. Model A. I like to put explanations. I don't look at this little tiny box. I didn't expect you to put too much of an explanation there. Oh, the explanation goes down here, huh? Okay, Model A. Why do you think it's that one? Explain why that one involves the most energy based on your understanding of the attractive forces between the electrons and protons in the atom. Think about the energy needed to push and pull. Again, a couple different ways of thinking here, but say Model A's electron moves the farthest toward the nucleus. Okay, if a student put this, what do you think I would say? Do you think I would say you're done? Probably not, right? If a student put this, I would say, why do you think that moving the farthest towards the nucleus, why do you think that has anything to do with energy? Well, you got to make that connection. If more energy moves the electron, you can also put E minus if you want to be lazy. That's an acceptable way to be lazy. If more energy moves the electron further from the nucleus, then a longer movement, or a farther movement toward the nucleus probably generates the most energy. Boom. You also could go with the the frequency and wavelength relationship. That would be fine. But I do want you to see that the wavelength and frequency and color of light relationship, all of that happens because of these little transitions that the electrons are making. So you can talk about this if you want. But this is the why. This is why those electromagnetic waves are being generated, and this is what determines what color they are, and this is what determines their wavelength, and this is what determines their frequency. Alright, finally, this is the last slide, right? This is the last slide. Excellent. Explain why you think a single atom of hydrogen cannot produce all four colors. Violet, blue-violet, blue-green, and red simultaneously. Hint, a typical hydrogen atom has 1 proton, 0 neutrons, and 1 electron. Explain why you think a single atom of hydrogen. So we've just got one atom of hydrogen, and it cannot produce all four colors. What does that mean? Why does it say it can't produce all four colors? We saw up here, let me go up a little further. We saw up here that this gas tube full of hydrogen can produce 4 colors. So why is it saying hydrogen can't produce 4 colors? Well, do you think this is a single atom of hydrogen in here? Or do you think this is billions and billions and billions of hydrogen atoms? Yeah, it's billions and billions and billions of hydrogen atoms. So it's doubtful that every single atom is producing all four wavelengths of light at the exact same time. And why is that? Well, in order for an atom to produce all four colors at the exact same time, it would need to have electrons engaged in these little transitions, right? It would need to be doing all four of these at once. Do you think one atom, one hydrogen atom, can do all four of these at once if the hydrogen atom only has one electron? Well, no. And that's the answer. You'd have all four electron transitions at once. And it can't do that because it only has one electron. And one electron can't do all four transitions. Make all four colors at once. 21. If a single hydrogen atom can't produce violet, blue, green, and red simultaneously, then how do you explain the presence of all four on a hydrogen spectra? Darn it! I gave away the secret ending, didn't I? Do you remember what it is? If a single hydrogen atom can't produce all four, and we're getting all four in the hydrogen tube, well, four colors are being generated by billions, maybe even trillions, maybe even quadrillions, I don't know. Billions of H atoms. Each atom could be in one of the four transitions at any given moment. And if you wanted to even be more specific, you could say at any given moment, some would be making red light, some would be making blue-green, some blue-violet, and some violet. Was that our four colors? Yeah, red, blue, green, blue, violet, violet. Okay. So there you go.